So last time we spent the entire class to talk about optimizers, and basically we look into like first order and second order methods. Like first order, basically just stochastic gradient descent and the variance, and then we spent quite a bit times on the second order. So let me just quickly went to the summary slide. So basically that is the actually by the way, I mentioned that the bonus is still on, although the bounty is still on if anyone want to solve this algebra here. And again, yeah, the problem is I start with this guy and this guy. After many algebra that I gave up, you should get something like that. Yeah. So and basically, yeah, you can ignore all these indices. Right? So bk plus 1 is the inverse of hk plus 1, and bk is the inverse of hk. So yeah, all the papers and references, they just say that using that you will get that. So I assume that it shouldn't be too difficult, but probably just quite tedious maybe. And so at the end, we said, okay, we have this Cauchy-Newton method. So okay, maybe I recap a little bit. The idea is like in second order, you have this Newton's method, like just in as in 1D case, like if you are trying to find a optimization of like maybe this 1D function, want to find the optimum, the minimum here, then the second order method will be like I will just start with some point here. Then at this point I use not just the slope, not just the gradient, but also the curvature, basically the Hessian, to approximate the kind of like parabola, or in this case it's a parabola, but in high dimension will be a ellipsoid. So and then you find the minimum there. You from this one, this approximation, you can immediately know the minimum is here, right? So the next step, you will start from here, and then maybe you have and try to kind of project or like approximate another parabola, and then like you go down and so on. So this is the kind of like 1D intuition. So in high dimensions, you need to deal with not the gradient, but you need to deal with, not to deal with the slope, but you need to deal with the gradient, and not the curvature, but the Hessian. And the Hessian will be pretty high dimensions, right? Because the gradient is just nd, but the Hessian is n by n. And just storing it is huge. Then we have so-called like BFGS and DFP is basically just kind of approximation technique that trying to approximate the Hessian by rank 2 approximation, rank 2 update. And if we solve the algebra like I showed you earlier, then you find the update and so on. And then like for the update, for example, like will be have update like like this one, right? And the problem is like still you need to store the Hessian or the inverse Hessian like that, and then this, because it's n square, if you have a million parameters, then the order will be, actually I said that last time was not correct. I said it's 1 tel, but it's actually more than that, because 1 Mach square will be like 1 Mach times 1000 is like already 1 giga, and then times 1 Mach 1. Wait, I got confused, sorry. 1 Mach times 1 Mach, is that, oh, maybe I'm correct, it's 1 tel, is that? Yeah, probably is right. So anyway, but 1 tel is still huge, right? So therefore, like, we mentioned that, like, we have so-called update, or not update, a improvement, enhancement of BFGS, known as LBFGS. Basically, we are not going to store this BK, but instead, what we are going to do is simply when we have the update like from the last iteration, oops, actually the previous update probably is not BFGS, but it's DFB, but it doesn't matter. So we have update like this. So instead of like using the previous value of BK, we simply use identity. Of course, they will be far off, right? But what we can do is that we can iterate more than one time. So first time we start with I, then next time we plug this back and iterate again, and then iterate like maybe 10 times. Then we will have a reasonably good estimate. But of course, like, then you kind of trade off time with accuracy, and also like actually trade off. Yeah, actually no, actually I trade off like time with space, or space with time. How do you say it? Anyway, yeah, I guess you understand that. Basically, like we the space. We trying to trade off the trade off the space with. Should I say trade off the space with time or trade off the time with space? Either one, okay, yeah. But in this case, therefore LBFGS, you expect the accuracy is lower, and the time maybe is increased a little bit, but you just save lots of space. So that's LBFGS, and it's actually popular, very popular. BFGS and BFGS is actually very popular in some sense, like in optimization. But finally, I also mentioned that actually I stumbled through this one a little bit. I guess I didn't articulate very well at the end. So if you think of like, I guess we mentioned a couple of times, machine learning and optimization is quite similar. Both we trying to, actually you can think of like many times when we're trying to solve a machine learning problem, we just ended up solving an optimization problem, right? But the difference is that like for machine learning problem, your objective function is really just an approximate, right? You only have the training data, it's just an approximate objective function. Now if you have this approximate objective function, and you use all the data full batch, then at least your gradient is exact. So you have the objective. We are doing the optimization function, optimization problem here, and you use all the training data to approximate your gradient. In terms of this approximate optimization problem, at least the gradient is exact. But now you can further simplify that. And actually, we always do that. It's like instead of using all the data at once to compute the gradient, we'll just use part of the data to compute the gradient, right? That we use the mini batch. Then in that sense, even the gradient in this approximate optimization problem is approximate again. So we have two layers of approximation. In this case, like BFGS is not very good because it relies a lot on doing your have accurate approximation of your gradient to approximate back your Hessian, right? So you do many iteration update to get that approximate Hessian. Then each time your gradient is already approximation, so therefore like you expect that approximated Hessian won't be very kind of accurate, and then just the outcome is that LBFGS in that case doesn't work very well. So therefore, like in mini batch setting, like this is not a very good solution as well, like for LBFGS. So in terms of machine learning, therefore, like it's useful, but oftentimes I guess people eventually just start with like Adam and for many of these problems. So I guess that's what I'd like to recap a little bit about optimization last time. Now let's start with something new and kind of important. I won't say a lot about this, but it's actually quite important. Is now you start training your data. I mean, you collected the data, you decided the model, now you start to start the learning process, and you really need to babysit that. And of course, we mentioned some of this step already at the beginning, not at the beginning, but previously. We will do some pre-processing often, but not as many pre-processings as in cell processing. For example, like it's not typical trying to whiten the data in the sense like do a PCA just to kind of rotate your data. Is that uncorrelate your data, and then I normalize that to become whiten the data. But typically we can just end up with satisfied with just make the data zero mean and then maybe normalize in each axis. So now after pre-processing that, then of course we need to design the architecture. So let's say we have a fixed architecture now, Wi-Fi architecture that we are going to use. Now we really start to training the model. So to start with, like it's good to just check whether your loss is reasonable. So for example here, let's say I have a 2-layer neural network that what was the model again? So we have 10 outputs, let's say 2 layers here, 1 hidden layer, and 10 outputs at the end, and we are using softmax. Now, and then we just pin out the loss at the beginning, so I'm check the loss value. For this one, it's good to us, so it kind of makes sense, because if we are using like softmax and if you remember, if we're using the cross correlation loss, sorry, not cross correlation, cross entropy loss, then the loss will be simply something like minus log p, where p is the probability of the I might put I here, pi, where I is basically the ground truth index there. Basically it's classified to this class, and pi is basically the empirical probability, or the probability that from the output of the network, right? So then if I started with the model kind of like in random, I expect this, if I have 10 classes, like all this probability will be roughly the same, so uniform. So then this would be approximately 0.1, 1 over 10. So if you compute minus log that, you should get like approximately, oh wait a sec, did I say, think correctly? I should get like, 2.3, I believe. Or you can go back and check, I guess. So next thing we may try to do is like, we may try to crank up the regularization. So typically with your regularization if you remember, like regularization will be like you typically have the objective function that you want to minimize the loss. For example, in this you have the cross entropy loss that, as I mentioned, I have this log pi already, something, and then I may have the regularization may depends on maybe just it can be the model complexity. For example, like the norm of the parameter, something like that. So if you add that, at least I don't know how we are going to add this, but we expect if we add the regularization there, I mean, okay, of course, like that regularization parameter should be here. So maybe alpha times something like that. So if we crank up this regularization parameter, at least we expect the cost to increase, right? The loss will increase. And again, this is a simple sanity check. Like we do that, we get a little bit bigger. This makes us happy. And then And the next thing like is also like very good to check and very important to check is you should not happy immediately and then start just putting all your training data there and trying to fit your model and train the model like and then like go back and drink a coffee and come back like next week and stuff like that. The first thing you should do is like you want to see if you can overfit your model, because if your model is sufficiently complex, basically you can always make your training error. It's just like you're fitting a line, right? If your model, if you have data points in 1D arbitrary data point, if your model is this is so ugly here, but it's okay. This is a point. Let's say I put 2 points here. So, but if your model is sufficiently complex, you can always fit the line completely for all the points, right? So in that case, the loss will be basically equal to zero loss. So it's the same in this case here. Your models is sufficiently complex, or your training data is sufficiently small, you can always overfit your model, right? So then it's very good to try that. Let's say just make very small example. Let's say just take 20 samples here and try to overfit the model, and then and be sure you don't want to impose any regularization, because the regularization will restrict your model capacity, right? So in that case, if you have the regularization parameters, you basically say I don't want have so many turn like in your curve there, so it will force to have some loss there, cannot fit all the data points there. So, but if you turn off your regularization, then you definitely can overfit your model. So then again, just check the loss. You should get very, very small loss. Like in this case, very small loss here, and we are happy. So next, next we can really start to do actual training. So, but we need to decide. Okay, the most important parameter probably is the learning rate. So we need to start with something. Let's just pick something at the beginning and try to see what's going on. So let's say in this case, for example, like now you see, okay, we work on that for so many epoch, and you can see the cost going down a bit. No, actually the cost barely going down at all. But actually the accuracy does go up. Right? The accuracy start with like, I'm not sure how good your eyesight is. Maybe at the back, not sure. What's your name? I forgot. I never asked you, I guess. Oh yes, no, I forgot. Yeah, you are Alfredo. Yes, yes, yeah. I'm not sure Alfredo can see it, but this 0.08, and this is like went up to like 0.2 approximately. But you see the cost doesn't change. The loss basically doesn't change, but you have this. The accuracy actually go up a little bit. Like, can you think of like why is that? Like, any possible reason? Yes.
I think the learning rate is too low.
Yes, the learning rate is too low. Yes, but one thing, yeah. I want you to pay attention though here is that like the learning rate, yeah, in this is probably too low, but you see that like the cost is barely changing here after several epochs, but the accuracy actually just went up a bit. So can you think of like it's went up quite a bit? It kind of accuracy got double. Can you kind of reason about that, like why it's possible like this?
Maybe the model is trying to overfit. So, so the loss computed after each epoch is not contributing to the error during bad propagation. So we probably need to add some regularization term, generalized better. I don't know. No?
Yes, actually, yeah. I guess this is actually quite difficult to kind of spot this honestly, but what's going on most likely is that if you think of, for example, we have 10 classes, right? So remember, like, how do we compute? Let's say we start with like this is what you have, the cat class is correct. Let's say a bunch of cats. We are trying to discuss all the ground truth here. So I have like all of them is more or less 0.1 or something like that, right? And I have this cat class is originally also 0.1, let's say. So, but maybe after several epochs, that when I train it, this probability went up a little bit from 0.1 to 0.101, let's say. Now, if you think of like what's the cross entropy loss, the cross entropy loss is minus log this p, right? 0.1 versus say minus log 0.101. So therefore, it barely changes at all. But this 0.101 is sufficient to push the accuracy up, because if you think of like what is the accuracy, we just count the one that win, right? So basically, this is the class that gives us the highest probability. Therefore, we design is the cat. And in this case, even though like it barely win over the rest of the class, we already consider it's a win. So therefore, like the accuracy went up. I mean, this accuracy, with this we'll consider as a correct classification. So most likely what is going on here is that you have several of these samples, all of them just change tiny little bit in the true classes there, such that like all of them switch from like incorrect to correct. Therefore, now the accuracy rate goes up, even though the kind of the cost, basically the cross entropy loss just barely change at all. Okay. Anyway, just let's move on. So as you mentioned, it's correct. Observation is like really the learning rate is too low. Then let's get it bigger. So now this is just kind of exaggeration and make it crazy. Just maybe the learning rate earlier say 10 to minus 6. Now it's just kind of like suddenly rise up to 10 to 6. Then of course it doesn't work. And typically when learning rate is too high, we'll just get a bunch of NAN. So most likely, like, yeah, actually, honestly, I'm not quite sure which part went wrong, but that's typically what will happen. Probably there's some CO somewhere that you have like CO over CO, that kind of stuff. But seeing this, like NAN is a pretty good indicator that your learning rate is probably too high. And I'm too high, so the cost exploded. So then next thing, yes, yes. So therefore, like, okay, one thing, when we train this kind of neural lateral model, we really need to like tune this learning rate very carefully. And typically, what people do is like they just simply try many different learning rates. And it's good to use a log scale. You can train, you try from, of course you can try like linearly, but it typically is more efficient. You try in a log scale, like 1 to minus 5, and then like 5 to minus 5, and then it's 1 to minus 4, 5 to minus 4. And one thing also, like this is how important, like it's mentioned in this paper. Actually, this is some of this mistake I made when I was a master student, also when I need to tune parameters. When you have multiple parameters you want to tune, it's pretty tempting. Let's say I have like parameter P and parameter Q, then maybe I just have 2 for loops here, like for P is from 1 to something, like for Q 1 to something, and then just look for all of that. So it turns out it's not a very efficient way to do that. The reason behind that is because like if you think of like maybe in some scenario, how do I say that? Yeah, like in this case here. So you have 2 set of parameters. They typically don't have like same importance there. Like some parameter may be more kind of sensitive. Maybe your result will become more sensitive to one parameter than the other parameter. So in that case, you probably want to have maybe the other parameters should be kind of tuned more finely, right? But we don't know that beforehand, right? So if you do a grid parameter like this, so it turns out that, like, as you can see, like, even though I sample same number of samples here, like I sample like 9 different sets here. Here also 9 different sets here. So the combination across this parameter for this one, actually, I only try 3 different combinations here, right? But here I actually indeed try. This you can say is pretty close, but they are still like different values, right? I'm more or less really trying 9 different values here. So therefore, if you have really one parameter is really useless, then in this case you're wasting like lots of computation time. In this case, like 3 times your computations just to tune this useless parameter here. Instead, you can be much more useful, like to. So in other words, like what you want to do is not always not to do a grid search, but you just randomly pick parameters over the parameter space, like that. So it's. Don't do a for loop, but just yeah. Yes.
I've read that you can also do a logarithmic grid search instead of linear grid search.
Oh yes. You actually I just mentioned it, but I didn't emphasize that. You most of the time you should always use the kind of like logarithmic, like log scale rather than like the linear scale. So this is actually a log scale here. Yeah, I should emphasize that.
Okay.
Yeah. And so very reasonable strategy would be you start from cost and then find search, where you start with some the cost search there, and then you not stop, but when you close there, then you swap to a final scale for a second stage. Oh, and there's also write down some tips here. If your cost turns out is bigger than 3 times the original cost, probably you want to kind of break out early. That you probably didn't pick a right parameter, and you're kind of exploding your solver. So here's example. Like he's trying to yeah, but here it doesn't use the log scale though. Here it uses uniform. It may not be the best strategy, but I think they are using unit from here, right? Let's see. So the learning weight is no, I think they're using log scale, but I cannot see the log scale anyway. Okay, maybe it's hidden inside. It's already log scale inside, I guess. So it's say from no, it's here. I'm sorry. Like it's here. It's 10 to minus something. Yeah. Okay. So it just, as we mentioned here, we don't use grid search, so it's randomly samples from basically the regularization parameter and the learning weight at the same time. And then I try a bunch of values within this range, right? 10 to minus 3 to 10 to minus 6, and this is 10 to minus 5 to 5. And can get like a bunch of like values here. And we got like these are the accuracy, so larger is better, right? So in this case, so this sample is pretty good, And then if we look at the learning weight there, it's about like -4 for this one, for the learning rate. The regularization parameters say it's in the -1 and -4 and so on. So then I guess they are in this case a bit satisfied with the range. So they from -3 to -6, maybe we can kind of shrink down a little bit to like let's say -3 to -4. And also the regularizer, like we don't need to go from -5 to 5, but just -4 to 0. Then and try again. Now the values get even bigger. The accuracy now is we get up to like 0.353 something. So this is the best one. Basically, it's 0.531. But Andre at that time have a remark here. He said that, but this best cost validation result is a bit worrying. Like, do you see like why he thinks that, why he thought that? Honestly, I think it's very hard to spot. He gave this question. I don't ever think anyone can answer that. But basically, it's not that difficult though. Like because the range here is like -3 to -4, so this is near the boundary there. I guess this is near 10 to -3, right? Near the upper bound there. So this is a little bit worrying. Maybe like you have the optimum parameters actually a little bit outside that bound. So then maybe we should push this up a little bit just in case and so on in the next loop. So but what I mean is like as you can see like he have this analogy like you are really, this is more like an art, like you have a lot of tuning playing with these parameters and not really that, I shouldn't say not really that much of science, but it's really a lot of art here. And parameters that we have to tune, that we mentioned, like regularization rate, learning rate, but also like don't forget about the level architecture also. Like of course we start with like some architecture, but maybe later on we decide that okay, this architecture may be not sufficient, we need a bigger level and so on. And also like lots of other stuff like drop out strange and lots of other parameters you can play with. And this is kind of crazy. That's what he did. So I guess like if you I don't know, but I guess like if you really going to go for a PhD in neural network or like machine learning, maybe you will eventually end up doing something like that. You just need to try a whole bunch of parameters, and maybe you need to have kind of something like command center as what he has. So it just control like each of different. Basically, here is like he has different node running different kind of optimizer, right? And then like some of this running pretty well, some doesn't work well. Then he just kill it, and then so on and so forth. And of course, like one very useful indicator of like how well you are doing is to look into the loss versus the epoch curve, right? And for example, this have like different possibility here. This, of course, this probably like you just suppose up like maybe even get to any end way earlier. This is like just the learning rate is too high, and maybe it's not extremely high, but reasonably high. You still have problem. Like at the beginning, you went down quite quickly, but then very quickly you just saturated. So you are near the optimum, but you just oscillate. Like around the optimum, you cannot go down. Of course, at this stage, maybe you can lower your learning rate. Then there's a chance you can just go down again. And of course, if it's too low, the learning rate will just converge very slowly. It will drop. I mean, the loss will goes down very slowly. And this is optimum, but it's hard to kind of obtain. This is another one he kind of show just for something to be interesting. Like, again, what do you think? Like this may happen, like to have a loss function, or like loss versus time curve goes like this. It doesn't go down for a long time, and suddenly decided to go down. Yeah.
Plus the exponential of verb, and like at 0 it stays at 1 or at its highest output, and then as it goes higher on that exponential, it starts to go lower.
That's a very good answer. I like it, but probably you think overly complicated about that. So imagine, I guess it's very good to imagine. It's like, think of like you are doing optimization. It's like you are driving a moon, like a moon vehicle or whatever. So exploring the terrain, and then you just want to go downhill somewhere. And also you're blindfolded. You can only feel the slope. You have scope, like tell you like what's the current gradient going down, and you know nothing else. You cannot see anywhere, and then just blindly driving this thing, or like maybe the robot driving that thing. So yeah, there's many possibilities for this one. One probably is just bad initialization. You start with a point, it's actually a kind of like a plateau, and then like you're high up, and then you drive for a long time, then suddenly you can start going down. But this just happens. So therefore, like initialization is kind of important also. Sometimes when it doesn't work well for your initial, even though you have this relatively intelligence already, like weight initialization we mentioned earlier, rather than just blindly put it randomly. But still, maybe like you start with something that is really bad, or like maybe it's not really the weight initialization also, but also the weight initialization. But then maybe you try another set of ways, then maybe just work a little bit better. Or maybe you can wait like this one, just keep running until suddenly you go down. He also collected. I guess this website probably is still running. He created this website, just try to put up all these real loss function there, and lots of real loss functions, and and of course this. One more thing is this is we mentioned earlier, this variance versus bias. What's that? Variance versus bias trade-off. So if your model is kind of, in this case, actually, by the way, it's like you have really large gap. Do you still remember that? Most likely it's like, if you think of in terms of variance and bias, most likely the model is, this one is like high variance or high bias.
Looks like high variance, right?
Is that? Yeah, I think you're right. Yes. Yeah. Yes. More like high variance. Yes, I think you're right. Yes.
Yeah.
Yes. Yes. Tosa, I want to say something also, right?
Yeah, I was going to say the same. So the more gap means biasness, the no gap means
yes. Yes. Yeah, I need to think actually. So anyway, yeah. So the rest of the guys is okay, right? Remember, like variance is high bias. I always remember high bias. Someone is really stubborn, right? He cannot learn, right? So therefore, it's high bias. So high variance has low stand basically. And in this case, it's like you give him whatever training data, you're just able to train. So, but it can fit very well with the training data, but it's just far away from the fact. So yeah, it's high variance. What else? I see. Another thing is like, besides checking the, absolute magnitude changes of those weights, oftentimes it's like it's useful like to check the ratio as well. Just basically to see like what percentage of your weight changes. In terms of percentage, I should say, like what fashion like the weights change. In terms of magnitude, like what fashion it change. And for example, like if change in this, maybe in this range would be kind of with about 0.01, or like around like 0.001, then it's somewhere like reasonable. So you don't want the weight just change like too quickly. So that's just a kind of summary of like we talk about for several lectures, just the vanilla plain neural network. So so some conclusions there. BP this is a take-home message. Especially BP. I hope that after like 6 months later, at least you can still say high level what is BP is to someone else. So it's really nothing. It's like that. It's used to compute the gradient for all the parameters. Oh, sorry. Let me say more clearly. We want to compute the gradient of the objective function with respect to like each of the parameter, and we use BP to compute that. And to compute that, the procedure BP is basically just chain rule in calculus. It's nothing really special. So if you go back to the nodes, and then it's just you have like gradient feedback from the end, like from the end of the network, and then the feedback gradient will just multiply with the local gradient, and then like feedback again. So therefore, like we call it backpropagation. And about activation function, I just start with value. Like most people just use value nowadays, and then that's other something similar to value, but you can start with value. So preprocessing, like we mentioned several times, like it's not really that important, or like it doesn't look like it help that much. Typically, we still need to subtract means, but it's not very useful to do any whitening. So basically, doing PCA to uncorrelate your data and so on. Weight initialization is very important. And batch normalization is also very, very important when you get to more layers. When, for example, like for Google Lat, I don't remember, like say 16 years or like 19 years, I forgot how many exactly. But they need to introduce spatial normalization to get into so many layers really. And use dropout and Atom, I don't know whether there are any new kind of optimizers, but apparently Atom is very popular and still many people like it. And if you don't have many data, then you can consider using LBFGS also. In particular, if you can do full batch. If you can only do mini batch, then it may not make sense in that case. And you definitely need to babysit your learning data. Your learning process. You cannot just put it there and drink coffee or go back 1 week later. Probably it just doesn't work anywhere. So it's a painful thing, but you just need to babysit it. And never use grid search for tuning your hyperparameters. And that's it. I guess I don't know whether I should start anything. So that's the plain vanilla neural networks. And so maybe I just start a little bit for the CNN. So next we are going to talk about CNN, convolutional neural networks. Maybe I don't know whether it's. So I guess this line put this slide on. Just want to say CNN is not something new, but as if you remember, we mentioned previously. And I forgot whether I mentioned that. I probably mentioned it in some other class or something. Of course, CNN typically the invention of CNN is credited to Yann LeCun. He is professor of NYU and also head of AI in Facebook now, Facebook research. Actually, I just met some student, not students, but some guy in Becker Hills last week that he graduated from NYU and he took his class and honestly I shouldn't say more, but he didn't like it. So he said it was very popular, but he said it's too difficult or something. But anyway, but if you search for Yann LeCun, he gives talks wonderful. Maybe his class is much tougher, I don't know. But he gave really good talk and stuff like this. Yeah. But also, actually, personally, I highly recommend there's an interview. You can look for interviews Yann LeCun interviewed by Andrew Ng or Andrew Ng. I like to call it Andrew Ng. Andrew Ng, I don't know why. It doesn't make sense to me. But that again is NG, right? NG, how do you call that? NG? No. This is the last name. Yeah. Yeah. So this is a last name. Okay, I talk about some Chinese now. So this is a Cantonese saying of a Chinese, something like I even can write the Chinese here, something like that. It's actually an Asian country in South China, something like that. But there's a surname for that. In Cantonese, we call or something like that. It's just have. So that's why when the British came to Hong Kong, the best thing they can spell it is NG. So, but back home we still say something or something like that, say Andrew or something like that. But apparently now here in the US, I heard people call it Andrew Ng or something like that. But anyway, and if you don't know, he was the he was a really successful businessman. He started as a professor in Stanford, but then when he was an assistant professor there, he already started Coursera with some other fellow. And of course, you know what's Coursera, right? Then afterward, he go back and forth industry, into Google sometimes, and then he also went to I guess a couple of years ago, like he just went to Baidu, that's like the Chinese Google, and was there like for 3 years as their like head of AI or something, for head of AI or head of research. But then he quit basically for ungiven reason. Then he just started deep learning.ai, something like that. So, but he and probably in that deep learning.ai, he had an interview with Yang LeCun, and that one is pretty nice, like half an hour. Like, I encourage you guys to listen to that. It's talk about like Yang LeCun, like when he in the 80s, when he started as a PhD student, and he have low access to all this idea. I mean, he is always interested in AI, and he didn't know anything about neural network. And then first time he saw something like that, he think, wow, this is wonderful. That's the way to go. Then he just tried to study all this by himself, and then he kind of I guess in the 80s. Backpropagation was not very popular yet. Not popular, I mean not very well known yet. In the early 80s, and many people thought that they created that or like invented that. Then eventually all of them realized, okay, this was invented in the 60s by some control guys already. At least not just invented, they talk about that already. And there was a paper by Geoffrey Hinton on backpropagation, in Nature or something. And Geoffrey Hinton, I think he went to France for a conference, and then Yang LeCun was there also, and then but they didn't met, and then one of his Geoffrey Hinton's colleagues met him, talked to LeCun, but he didn't talk closely because he realized that he was working on something similar, because he also Yang LeCun we invented BP also. So therefore, when Hinton's colleague go back to U.S., then he told him this French kid is doing exactly the same thing as we are doing. And then the next time Hinton went there to a conference also in Europe, he just said, who is Yang LeCun? I want to look for him and stuff like that. So, but many years afterwards, he's successful and went to Bell Lab, at the beginning, I guess he was really successful in Bell Lab just for the first several months. That he mentioned that he was also working in Toronto. I forgot where. Montreal or something. I forgot. He was for a while, and he mentioned that in the department, the whole department only have one workstation. And then once we went to Bell Lab, he asked the manager asked him what do you need? What do you need? And then he said, I want this workstation. And his manager said, yeah, just buy it. Then he said he has that workstation on his desktop, and in some other university, the whole department is sharing that thing, and he was very productive for the first couple of months. And basically, they are working on this. Digital recognition system. They already in Bell Lab, they have all this data already accumulated to do postal recognition, and then he therefore he has the data. He has everything he understands. So you just need to code that. But of course it's not like now you have all these packages, right? He need to code from scratch to use C and so on. It took him 6 months or something. And then he got a really great result, and then he got to conference, and then beat all the previous previous approaches. And then he met Hinton again. Hinton just told him yeah, you know what? If you do everything right, you just expect good results, something like that, right? And and then the story didn't end there. The story continues that Bell Lab got speed up, not after just several years later on. I'm not sure by that time they have everything built up that they're trying to kind of sell the algorithm or whatever. But unfortunately, the algorithm somehow went to the company not in his group. So he is another group, and this pattern just went to another company. And that other company had totally no idea what CNN, then just stuck there like for many years. So that was like talking about I don't know late 90s or like early 2000. I don't know when. I don't know. I forgot when. Like when did like AT&T broke up or like anyone remember?
I don't remember.
Yeah. So but anyway, like and then from another talk, I remember LeCun. He kind of not exactly complained, but he kind of what should I say? Like I cannot find a good English word for that. But anyway, mildly unhappy about like he actually, if you remember, like 2012 is actually the kind of Leo Electric get back to mainstream the year. Because like that's in the image that competition, you have this approach in CNN and Leo Electric based on Leo Electric just beat the other approaches like by a really wide margin, and then afterward everyone start to look into Leo Electrics again. Even though like people in the, inside the more like Leo Electric group, they restart all this research in mid 2000 already, but it didn't get into the popular attention till 2012, right? But actually, LeCun did submit same thing in 2011, and the review just don't trust the result. Basically, say, we don't know what's CNN. I never heard of that, and then like, so the paper got rejected. So otherwise, that starting point will start from not 2012 but maybe 2011. But actually, even in 2012, like that's Alex that way. I forgot his last name. His last name is complicated to me. Anyway, Alex is a student of Hinton. Also was a student of Hinton. I heard story that like when he presented like his work, also like he was thinking, because he worked on this for many years, right? He was thinking like everyone knows what's CNN, and he talked about it like everyone knows what's going on, and of course no one knows what he's talking about. So, but at that moment, like, it just changed everyone's opinion that like, oh wow, we really should start working on this thing. So then, yeah. Anyway, so but if you look at this year here, this LULAB thing, like LeCun is really day back. So this CNN thing is really not new. And if we, oftentimes if we talk about history of the CNN, we will kind of like quote back even to this Hubble and Wiesel paper, this in some biology journals saying like they do experiment on this cat and try to probe into the brain cell and look for stimuli and see for different patterns, and then like by accident they see a line there, and then they manage to get all this activation like stimulus like somehow, and then they also conjecture that like they have seen some hierarchy in the kind of visual cortex, like from this so-called lateral geniculate body, simple cells, complex cell, and then like higher and higher orders and so on. And until like Fukushima, that's in early 80s, like he kind of borrowed some of this idea of I don't even remember the name. Yeah, Hubble and Wiesel, sorry. And of course, from the name, you know that he's a Japanese guy, Fukushima. We have this disaster in Fukushima. But I don't know, I'm not sure how many people actually read the paper. Before this class, I tried to run through the paper really quickly, but I don't get much out of that, honestly. Basically, he want to create a system similar to this layer system, and then he want to do have like layers of simple cell. Basically, he has a simple and complex cell like sandwiches, And simple cell is like doing kind of like the neuron things, and then the complex cell is like doing polling. I guess the main thing is like he realized that like for the visual operation, or for a neural system to manage visual data, it should have some spatial invariance. Right? If you have an object here, if I shifted that a little bit, I shouldn't process it like totally different things, right? So in the sense, I actually, the whole idea of CNN is very natural. It's basically just saying that why CNN, if you guys know a little bit image body computer vision, it's just a convolutional filter, right? And the convolutional filter, the presumption, the premise is basically saying that, okay, my filter is independent of where we are, right? Like I span over the entire space here, I'm using exactly the same filter, right? I don't change suddenly. Here I use a low pass filter, and I move a little bit, suddenly become high pass, and so on. So that's basically no reason for that, right? We have exactly the same filter and all over. And actually, CNN is nothing special in that aspect, like totally the same as like cell processing. The only difference now is in cell processing, you have all the design filter, Gaussian filter, like Laplace filter, and so on. You have the well-defined shape, parameterized somehow. And here, we just make it totally not random, totally trainable. So we have the filter there, can be anything. So because it's like what we have for the rest of the neural network, right? Everything is trainable. So and then this mention, of course, I did Lalufai paper. Actually, I think this year is probably incorrect. Is that using 1918? I think he may be. I need to double check. I think this is 98. Yeah, yes, this here, right? It's more like that. Maybe he has some published something like. Yeah, I'm not. Yeah, I don't think he did that at that time. Yeah, but anyway, I think it's more than 1908. Yeah, this looks pretty complicated. I don't know what is going on here. I will talk about this later on. Yeah, this seems to me is like. But of course, you need to have some pre-processing step just to segment the digital. This is basically just do the segmentation. Typically, we don't worry about that. Like in this aspect here, we just assume things like this probably we should worry about that in the computer vision class, like to segment all the digits. But here, like we assume like everything now is like is aligned register. Then like now we're going to do the detection now. So we have this. Every segmented digits now go to here and do the recognition. And then moving forward, we have this Alex Ladd we mentioned earlier. Krasavsky, yeah, I always don't remember. Suskiva is also, I don't know where is Krasavsky now. Suskiva is also very successful. I think he, I'm not sure he's still in OpenAI. I remember it seems like he founded OpenAI. Yeah, he's a co-founder.
It's very funny right there, Alex. That you would think that Skynet was taken.
Yeah. Nah, I don't think it's so. Actually, I think it's very unlikely, honestly. How many of you guys actually believe that? Like, we are close to that kind of like singularity. Sometimes people say that. I feel it's actually quite far. I mean, we have all these neural network things. It's do something really amazing, but if you think of that, it's still statistical techniques. Right. Just because you gave enough data there, it works, but there's no actual reasoning there. Like consciousness is really hard. And consciousness, or like just simple reasoning. I remember also like one example that you I forgot like which one mentioned that. Anyway, one of this big guy, I forgot which one. I listened to lots of these kind of interviews. I forgot who said that. He said that like he went for a vacation and sees just some kids like playing like what's that called? Like I always forgot. What's that called? Tic-tac-toe. Yeah. Tic-tac-toe or something like tic-tac. Yeah. And he said that like, okay, we have machine can beat human on Go, on the game of Go, but he probably cannot beat child with even tic-tac-toe. The thing is not saying that they cannot beat it when you describe all this rule clearly, but what he is saying is that like some kids just like playing in front of a hotel kind of like or like in front of a beach, and then I just with a stick and draw a grid and then start playing. The problem is like now you need to have the machine first realize that they are playing that game, right? Yeah, the problem is like we are still quite far from when everything is well defined, then okay, the rules is like that. And we think of the AlphaGo beat all of us in playing Go, but they don't know what he doesn't know what is Go really. I mean, I don't know, maybe I don't know, but anyway, like my feeling is like we are actually very far from my Skynet. But anyway, and I'm actually I don't know because we're out of time and I tell one more story, actually story. But I watched another video yesterday, so a random YouTube video that talk about exercise is really good for health, not just in the regard what should I say? Kind of to get not get overweight or stuff like that, but more or less saying that like it's good for the brain, because ultimately, actually that's also like related to another interview I listened to like by some I think MIT or like Stanford professor like biology professor or something like. She kind of like is a biology or like neuroscience kind of people or like psychology, I forgot. She doesn't believe that like we can imitate or create an artificial intelligence if we bypass the body. I mean, ultimately, the function of your brain is to keep your body like working. So, and why exercise is helpful sometimes is like actually the brain need to spend lots of power to do so. I mean, like it's very expensive to maintain the brain, and all this complex motion is actually a very difficult task for the brain, and if it realize that you don't actually need those motion, it will just stop spending resources to grow the brain or something like that. One example is the koala. The koala, because like after like some kind of evolution, it doesn't need to. I mean, it always eat the same kind of like leaf, right? I mean, it doesn't need to move a lot. And as time goes, like its brain just shrink because like, it doesn't need all this complex motion or stuff like that. So what it means, like therefore, maybe I should just stop here. But yeah, probably like we will need to have a body somehow, or at least like to really have like a general artificial general intelligence, like create a robot body for it, and yeah, I don't know. So anyway, we'll just stop here and we'll talk later.